Hi everyone, welcome to your favorite learning place. Welcome to Electronics with Professor Mughal. Well, I just assumed that you like me. I hope that's the case. Okay, so today is the first day of our lecture seminar series where I'm inviting people from industry ranging from aerospace to semiconductors to artificial intelligence to energy industry. These folks will be here to share their engineering work experience, career prospects, job prospects, and what to look for in an engineer. So if you are trying to find a job, or if you just graduated or about to graduate, you don't want to miss out on what these folks have to say about finding a job, how to get in. Okay, so our first speaker for today is actually Mr. Umair Zia. He's a director of the Distributed Energy Resources Department at Eversource Energy, and he's going to talk about some of the challenges faced by the utility industry and how they are working on different kind of renewable energy projects to increase energy capacity so that they can produce a lot more green energy and offset CO2 emissions. He's also going to talk about some of the job prospects, career opportunities in energy industry, and what he as a recruiter actually looks for in a fresh graduate. So without wasting much time, we'll get started and listen to what he has to say. Well, hold on, where are you going? Don't forget to subscribe to the channel.
To the end users. The system that we have today existed really for the past 100 or so years, ever since the turf wars between Tesla and Edison, where, as hopefully you all know, what transpired with those, where alternating current kind of won the race, and Tesla's alternating current kind of won the race into building the system that we have today. And one of the biggest reasons for AC to take precedent over direct current system was AC's ability to be transported for longer distances with minimum amount of losses. With direct current, if we had chosen that as our system, we would have ended up having to build generating plants very close to where we needed the load. And obviously, as you know, that historically up to this point, before the whole advent of renewable energy, the majority of the power production, had been from resources that somewhat pollute the environment, right? So we've had coal as being one of the major producers of electricity. And naturally, with AC, you want to build those power plants far, far away from where we live, where we want to use electricity. And with alternating current, you can transmit that power without losses to those areas. Again, if it was DC, you would have seen coal power plants all over where major developments are, thus further polluting, and you would have needed a lot more wires in the street. If you search for some old pictures of the electric system, the first ones that they built, in New York City especially, you'll see that, right now you see maybe one conductor, two conductors on a series of poles. They had 10 in series. That's how much you would need, kind of to use the DC side. So I just wanted to kind of set that premise and say that for the past 100 or so years, the system had been as such. Whatever was designed, we continued to kind of expand and build on it. It didn't really go through a lot of significant changes. Up until about the 1990s, we had a major revolution in the telecom industry, right? And communication kind of blew out of proportion, went from landlines into this whole wireless, saga. So what happened there and what happened with the whole dot-com boom in the early 90s is what's happening with the electric industry today. We're starting to build on the advancements of the telecommunication industry, the advancements in the computer electronics fields, and now kind of building what the electric system is. And of course, the whole new advent is on renewable energy. So most of my talk today is going to be about what's happening with the various renewable energy, kind of this force that's bringing us towards a lot of solar production, wind production, battery production, etc. What does that mean for the way power gets distributed today? And more interestingly, what sort of new challenges that's bringing, and thus that's where you guys come in, of what the future needs of the industry looks like, what sort of kind of the techniques we're looking for, what sort of knowledge we're looking for you guys to bring to the table. Again, the utility, what it was kind of, we were just building on what somebody else has already thought of, to now everything is changing so rapidly that we need some fresh ideas, some fresh thought, some new dynamics to the way we build our system. Does that make sense so far? Okay. So Eversource, the company I work for specifically, we serve the 3 states, Massachusetts, Connecticut, and New Hampshire. The map here shows in green the electric areas where we are, orange kind of the combined electric and gas. And last year we ended up buying actually the largest water supplier in New England, our privately owned water supply. So we have now all 3, electric, gas, and water, in our portfolio. And early this year, we established a 50-50 partnership with a European company called Ørsted. Ørsted is the biggest producers and installers of wind energy in the world. The majority of their plants are offshore. Plants are in Europe. They're now exploring certain offshore areas of Asia and Australia, and they also wanted to penetrate the U.S. market. They ended up winning a few bids. So if you look at what's happening on the offshore side of the business, there's been proposals to install significant hundreds of megawatts of generation offshore of the entire eastern coast of U.S., from Boston all the way, at least we're now down to Maryland. And Ørsted have won several parcels already where there's going to be starting installation. So we established a 50-50 partnership with them where they would put the wind generators, and we would run the cables and bring the power back onshore and then supply and distribute it to the customers. So again, kind of exciting to shift from, where we historically were taking our energy from coal, nuclear, hydro, shifting a little bit, not necessarily shifting the hydro, but definitely shifting the coal over to wind and solar. So that's kind of our footprint. Talked a little bit already about how power is the traditional system, a very one-way, from a power plant. We increase the voltage, and again, simple formula, you want to increase the voltage to avoid losses, reduce the current. So high voltage transmitted to what we call substations, and then at substations, very large transformers take that high voltage, which is at hundreds of thousands of volts, and put it down to what we can transmit on the wires that you see on the poles outside, which normally is about 13,000 volts. And then from 13,000, you see the transformers on the poles that then take the 13,000 and turn it down to what we can use in our outlet, so 120 volts. So very simple system, very one-way power flow is what we had. And again, like I said, what started to happen with the advent of the telecommunication industry booming up started to allow us the opportunity to modernize the electric grid. But back from 1990s and still, a few years ago, all we had done really is took what used to be a very manual system and turned it into an automated system through the use of different types of telecom mediums, whether it's radio or fiber, et cetera, et cetera. So let me give you a simple example. When an outage happened in the past, first off, we would not have any idea because there were not enough sensors on the system to know exactly who have lost power. So we rely on the end users to give the utility a call to say, we lost power. Then a manual troubleshooting sequence takes place where an actual person goes out with a utility truck, try to troubleshoot where the outage had happened. And once, let's say, a tree fell and took down wires, right? Now, the circuit itself is miles long, so the person has to sort of drive and figure out exactly where that fault happened. So that takes time, used to take time. Once that's figured out, then we had, sort of these manual switches on different parts of the system that individual would then go and operate and isolate that issue in a, as limited amount of area as possible, right? But again, that's a very manual process. You're going and actually flipping switches, larger switches than what we see here. But again, driving, traffic, all of that used to take a lot of time. With telecom automation, what we ended up doing is installed, kind of had all of these switches, all of our system integrate with each other, built a sequence that automatically now detects where the fault has happened and then reconfigures itself in literally seconds, right? So we used to take hours to restore the service. Now we can isolate the fault to exactly where it is or as minimum amount of a region and restore everybody else through different circuit ties and whatnot, right? So that was one step forward from the old historic grid. Still though, a one-way power flow. What's been happening really in the past few years, and it's picked up, is the end users with the state policies and whatnot are starting to install various renewable energy, solar panels on their homes. You see, as you drive through the state, you see large solar farms building up. You see wind picking up everywhere. And now companies like Tesla are bringing batteries. So historically, where customers used to have this, gas generator that they would only use when the utility was cut off, now the battery is running all the time because you don't want to just use the battery when you lose power from the utility. You want to use it every day. You're charging it with your solar. So why would you want to, sort of rely and pay a bill to a utility? You want to maximize the use as much as possible. And you want to take that excess stored energy that you have and you want to sell it back to the utility and further make money. So a lot of customers, hundreds of thousands of customers all over, are starting to install renewable resources. And, it's a great thing because it's clean for the state, it's clean for the nation, and we want to, of course, encourage and promote that. The challenge that now it brings to us, the engineers, is a very interesting one. We have this massive system that we built, and it took us 100 years to build and perfect it, was really designed and engineered for one-way flow. Now having to take energy back and work in harmony. So that's the new challenge. And it's not, historically, it was a very thought-through approach on exactly where to put a generating plant, how it's going to flow, etc. Now it's sort of ad hoc. Anybody, anywhere can pop and bring this renewable resource. And, our challenge is keep the existing system and add on devices, add on automation, add on AI for it to be able to work with what's happening with the renewable revolution. Does that make sense, kind of, with the premise? Cool. All right. So this is a good chart that kind of shows in New England, back in the 90s, we only had just a handful of grid-connected generators. very, very few CHP power plants. Some large facilities, such as WPI or Harvard had a CHP plant. Very large facilities would have these backup generators that they were connecting back to our grid. 2018, 125,000, right? Significant increase. And the numbers I'm going to show you later will tell you that even in the past 1 year, we had, this is going in a not in a linear fashion, in a very rapid increase on the number of devices that are connecting to us. So again, talked about this. All of this is coming from the states and countries' targets to go more renewable, to go more clean. And again, we as engineers want to definitely support that and figure out. And it brings a lot of interesting challenges for us on how do we make this happen, right? It's pretty exciting work. I'll skip that. So I talked about the numbers. Just let's focus on one area here. So if you go back to the Eversource system, just look at Massachusetts, right? In Massachusetts, we have sort of the separation between what we control in Western Mass and what the territory is in Eastern Mass. Everything in the middle is another company, National Grid. You may have heard of them as well. And they're going through the same exact challenges. I want to focus on the Western Mass area. This is, as you guys hopefully are familiar, it's a very rural area. A lot of land is available, but historically, there hasn't been a lot of load there compared to major cities, right? So if you look at the amount of megawatts of generation, and this is mostly solar, that we have installed on the system, connected, this is all customer-owned generation, 375. And this is what I'm currently processing in applications, and we're going and giving them authorization. Additional 553. This data, to tell you, is from June. In the past 3 months, this number has now reached about 650. That's how rapidly it's increasing.
Almost double.
Yep. So take this number, take what's installed, and look at the all-time historic peak of the electric system. So the peak is what the users have used in the past. This is what, when we are using electricity today, this is what the demand of the area had been. This is what we were buying from all the coal power plants, et cetera, right? To supply to the customers. The historic peak, and this happened back in 2006, back when there wasn't much solar on the system. The peak happened, it was 854 megawatts, right? This means this was the brightest, hottest day when everybody was using their air conditioning units, etc. So that's the maximum. This means that on a regular day, such as today, when the load is relatively low, the demand on the system is usually around 300 megawatts. But if you look at solar, look how much solar is connected. It's exceeding where the load had been previously. So if natural response is, well, we don't need our reliance on the other generators anymore, right? We can use all of this solar energy to supply our historic demand. The problem is, and the challenges, which I'm going to talk about later, is that A, it's being built in open areas where there is no load. So to bring that to where there is load is challenge number one. How do we do that? Remember what I said in the beginning. This is all DC production initially, right? DC needs to be closer to the load, not far away. So we need to figure out how to transport this to where the actual need is. B, what else is wrong with solar? It only, yes, go ahead.
The main issue is that, like, solar, it's, you can only generate power while, what do you call it, while there's sun out.
Very
There are
good.
batteries to
Yep.
store it, but they're not really cheap enough yet.
Excellent point. Excellent point. But they're becoming cheap, and they're bringing really good solutions to the even the first problem. There's a lot of research being done on superconductors that can transport energy without significant losses for longer distances. So we don't need to necessarily build these substations to boost up the power. So there's work that's going on there. So good point. So that's a couple of issues with solar. And then it's not only when the sun is out, it fluctuates even during daytime when there's a cloud cover passing over it, right? And I'm going to give you some real data that shows exactly how much significant that fluctuation is. So all of these are new challenges. All of these are issues and that much fluctuation on the system causes power quality issues, right? So we don't want, who would want to have a flickering experience? Imagine if these lights were flickering all the time right here. You won't want that. You want stability. You want stable system. So how do you take a fluctuating production and stabilize it? So that's issue or problem number 3 that we're trying to solve. So I just wanted to kind of highlight, there's, again, in other areas, there's a lot of megawatts that we've connected, but the Western Mass really drives the point home in, what's been happening with this renewable revolution. These are just maps giving you further details of where we've connected the megawatts in each of the areas. So again, let's look at Western Mass. The highest penetration that's going to be is in the Berkshires. And as if you've traveled to Berkshires, there isn't much load there, right? It's just open land, open country. So interesting challenge. So let's talk a little bit elaborate on kind of the problems that I mentioned. The first one being, again, the infrastructure is being built for these renewables where historically we had less load. The other is what we call this duck curve phenomenon. So historically, we've sort of known where, and we've learned over the years the usage, how the customers use electricity in the aggregate. And we can predict in advance how much load is going to be on a given day, at a given time, on a particular part of our system. And we had told the power plants to produce only enough power to support that prediction in the past, right? Again, historically, and as you rightly mentioned, even today, the batteries, we're not there yet with the batteries. Electricity was not being stored in the past. So we couldn't produce excess power, store it, and use it later. But rather, we had to produce enough that we were predicting to use. But with so much solar on the system now, that prediction is getting more and more difficult and challenging. So one of the things that's depicted here is what we call the difference between what the true load is. So take solar out of the system is what our historic projection had been on the system on a given day, and this is hours, and this is load on the system, to what we actually see because of solar on the system at a given time, right? And this is just prediction on, depending on how much gigawatts of solar is generating, how much load gets masked. And this phenomenon, just because it looks like a duck, we're calling it the duck curve. What could happen is, so this is an actual data on one of our circuits that, this was prediction, this is reality of what's happening. This is load prediction and actual load on the system without solar, and this is what we saw on that given day with solar on the system. Now, on a very bright sunny day when there's no cloud cover, sure, we can still have some sort of a meaningful prediction of what that's going to be, knowing how much solar we have connected. But now look at what happens when it's a cloudy day. Imagine this much fluctuation happening throughout the day, and then further, and this is system-wide, on that particular circuit. Now go more granular down to every customer, and if there's heavy concentration of solar in a particular area or in a particular neighborhood, that's going to see a lot more fluctuation or issues as a result of that. So huge difference. Same circuit, same time period. On a mostly sunny day, still relatively clean kind of the output. On a very cloudy day, you see kind of the ramp rate, right? So that's one major challenge that we're starting to see already on our system, and our engineers are solving the problems on how to handle this. When we do our prediction for any new solar generator that comes on our system, it brings an interesting question on, how do we predict in advance how much fluctuation that particular area is going to result in as a result of, kind of this cloud passing over it, and how many additional units that are already connected that we want to incorporate into that calculation. Can you predict a cloud cover? Can you predict how big it's going to be? Can you predict the speed of it, right? So all of that is now starting to play a major role. And interestingly enough, the professor is actually helping us with that research and trying to help us with doing some sort of advanced predictability so we can do meaningful flicker calculations before we interconnect new generators to the system or new solar sites to the system. I just threw this in just for fun. A couple of years ago when we had the solar eclipse in this area, so you clearly see when that came in, took the solar off of the system. Here it is, sort of a relatively cloudy day. Eclipse kicks in, takes solar off totally, and then comes back. So just a sort of a fun slide here. And then the last issue that I touched upon is power quality. So let's go back to kind of this traditional grid. Again, one-way power flow was very predictable. We knew exactly how much load we were connecting, where we were connecting it, and as such, we had to our disposal various products available that we could install in a very strategic location with predefined settings. Again, because we knew exactly where the load was and how it was going to behave, we could do a very analog predetermined setting on our system through the use of those devices. A couple of those devices are at our major large substations on the transformers. So the transformer output, as I mentioned, the ones you see outside, takes 13,000 volts, puts it to 120, right? On our substation, same concept, much larger system, but we don't want to set it at just one point because they're serving a lot of customers who are using, kind of a little bit on a different format throughout the day that the changes are happening. So the way those transformers, these large transformers were designed, that they had a component called tap changer. What that is basically saying the input is X, you want the output to be Y, but instead of just a singular Y, you want the output to be at multiple ranges. You can have an output of anywhere from, 13.2 to 13.4, 13.6, etc., etc. Because you want to be able to change that as your load is shifting. Because on a particular system or a particular circuit, you have residential customers, you have commercial load, you have universities, right, very large commercial loads, and each one behave a little bit differently. So the localized transformers, the small ones that you see, are dedicated for one type of customers, so they don't need this change. The large transformers at the back of the system that are supplying multiple different types of customers, you want this variability. So throughout the day, in the morning, you may not have a lot of residential load, you may have a lot of commercial load. Vice versa during nighttime, etc. Right? So you can do that prediction. So tap changer was there, but it was still a very static device. It was preset. We kind of knew exactly what that load change is going to be, and we could set that parameter in advance ahead of time. So that's device number one. Downstream of that, let's say that device is not itself sufficient. We had other equipment that we install on our system. A couple of devices, one's called a regulator, another is a capacitor. Same concept as you're going to learn in microelectronics. So take those devices and just expand it in a much larger kind of system, right? But conceptually the same thing. Capacitor, it stores energy and it stabilizes the output depending on what's happening. Same thing with the regulator, right? All of these systems were designed for, again, what? One way of flow. Now with the generators, when the backflow is starting to happen, these devices are getting confused, and rightly so, because they weren't really designed for that, right? So they're starting to get confused. If you had built this device to operate, let's say, 10 times a day, changes, now starting to make 100 changes in 1 hour, you're going to, A, burn that device a lot faster, B, right, you're probably not going to be able to produce the output very effectively. So what it's bringing is, again, interesting challenges for us engineers to figure out how do we, in lieu of just completely destroying the existing system and starting from scratch, use the existing infrastructure and bring the new devices to start to work in harmony, right? That's our challenge. Anybody can build it from scratch. That's the easy part. The hard part is take what's already there and not let it get destabilized, continue to still supply quality power, but then at the same time get the new renewables integrated into the system. Everybody with me so far? Make sense? Okay. So all this is showing is kind of how we were presetting our system to, a certain range to operate under, a certain bandwidth to make sure that every customer receives quality power. So moving towards this modern grid, one of the very exciting projects that we're working on, and it's sort of a very R&D type of a project, is taking a bunch of these different circuits that have this older system, older equipment. Think of it as we're adding some brain power to each of these devices, so retrofitting them in the field. We're adding a bunch of sensors across the variety of points of the system, and then bringing all of that information back and using, a new program, writing new code, making the older equipment to work in harmony with each other. So instead of just having preset settings that were very localized to each equipment, now we're saying, why not make every one of these devices to talk to each other? So as this fluctuation is happening, instead of them getting confused and just operating under their old conditions, so now they can talk to each other and come up with what is the most efficient way or the efficient setting for each one of them to have and hold and maintain throughout the day or throughout every minute, right? So that's kind of this R&D work that we're doing. We took a bunch of different circuits and we're kind of retrofitting new, older equipment, adding some more sensing devices, and we're gonna see whether our code works or not, refine it a little bit, and then move on, kind of expanding that experiment throughout the rest of the system. So that's one exciting project. We're calling it the volt var optimization essentially that's what capacitors and regulators do. They manage the VARs on the system and voltage of the system, and we want to optimize it. But rather than singular device doing it on its own, 100 devices are going to work in harmony with each other. Right? So that's one. The other exciting project that I want to just touch base on is, and somebody mentioned battery, right? You mentioned batteries. So we are at a stage where some of the batteries are starting to provide some meaningful, output, and the economics are starting to make sense. So I'll give you two examples of mega projects that we are currently working on that would go into energization in the next 2 years. They're in building right now. Engineering is mostly done on them, and we're starting construction. So, how many of you have been to Provincetown? Visited Provincetown? No. You should go. Whale watching. If you go there, if you're driving there, especially, right after about this area of the Cape, there isn't much load out there, except all the way until Provincetown, the town itself, has meaningful load. But again, this is a very rural area. And historically, if you look at our electric system, we only have one single line that goes from this point, right out here, all the way to the edge of the Cape, right? So what had happened previously is that if there's any fault on that line, for whatever reason, it takes out all of these customers. And because it's only one supply, there is no backfeed or tie, we can't pick up the load from anywhere else. So everybody remains out until the repairs are done. And usually the repairs take, a few hours. It could take 6 hours, 10 hours, etc. Right? So that's not good, right? If you live in Provincetown, you would not like that, of course. For us to provide redundancy, there's a couple of options, right? So let's think this through. Let's do quick engineering. We can run a second line. Oh, and by the way, the first line is on the overhead poles, right? It's on the overhead poles. We can run a second line. What would be a negative of running a second overhead line?
Vulnerable to trees falling.
Yes. So the same thing that's taking the first one down is going to take the second one down, right? So that's not helping. The second option is, okay, instead of overhead, let's put it underground, right? What's the negative of underground?
You have to do a lot of digging up, and
Yep.
it takes a lot of work to implement.
True, and it's very expensive, very expensive. And second, in this region, it's a very sandy region. So the digging is, even underneath, you're almost going into, you're going to get flooding into the system a lot. So that's another additional challenge. The other thing we could do is, which is even more costly, is bring a transmission line under the ocean, under the bay, from Boston into the Cape, but that is even more expensive than doing the underground system, right? So we don't want to do that. So historically, we've just sort of kept it at a single line, and that's how the system had operated. Now with the battery technology, of course, that provides a new interesting solution. So what we're doing is we're installing a very large battery at Provincetown, at the very edge of the line. That battery will get charged regular time when we have that singular supply. We're going to keep that battery charged, right? In an event, we lose that supply, that battery will kick in and provide a backfeed into the rest of the system. we're building the battery to operate for at least 4 to 6 hours, based on the load projections. So 4 to 6 hours, it's about the time that we're going to take to make repairs on the damage, and then we can flip it back. So that's one interesting solution that a new renewable revolution is now starting to provide, and we are taking advantage of that on our site. Similarly, a second large battery is going on Martha's Vineyard. How many of you have been there? Good. We all got to travel. So on the vineyard, historically, we had 4 transmission lines that go from mainland over to the island underwater. Okay. Very old system, but still very reliable system. In addition to that, we have old gas turbines on the island itself. So remember I said that electricity, historically, we couldn't store it, and we had to really predict how much production we needed. At the end of every system, we had these very small generating plants. The large ones are further out. They're running mostly 24/7, 365, because we know that at a minimum we're going to need X amount of energy across the state at a given time. So we're constantly running those systems. But then the variability has to be managed, and we don't want to shut off very large power plants. Those are very large machines. It takes time for them to get into a frequency that we want. So you don't want to shut them down and turn them on and off. What we used to do is have these smaller power plants situated in localized areas so that they can be run up and down depending on the localized need. So similar to that, we had a gas-run, very small power plant, probably the size of just this room. It's run on diesel, similar to kind of generators that you guys have in your houses, right? Same concept, it's just a diesel plant. It's old, it's rusty, it's sort of at the end of its life, so it's a matter of, do we replace that? Second thing that has happened is the load has increased on the island. So if we were to replace it, of course we were going to build a little bit of a bigger generator. That diesel doesn't burn very good. It's causing, it causes pollution. And a little island like Martha's Vineyard, it causes pollution, right? So that's not good either. What we could do is run a 5th transmission line from mainland over to the island. That's one solution. But again, historically, that had been sort of ruled out because how expensive it is to run underground system and maintain it. So again, what comes to save us? Battery technology. So we're putting a very large battery on the island. Same concept. We're going to store excess energy through the use of the 4 that we already have. We'll save it, and during peak times, we'll just dispatch that battery to keep the load where we want it, right? Make sense? Okay. Outside of our company, another interesting thing that's happening on the island is the transport authority, the bus service that goes around the island, is putting solar and battery all over. At their depot, they're putting solar and battery. They're going to change their buses to electric buses. They're going to charge the buses, overnight. And then as the buses travel, they're building charging pads. And I don't know if you guys have seen those in Europe. They've already instituted them. They're going to embed this wireless charger technology, same concept, embedded in the concrete. So as the buses come and stop to pick up passengers, it's going to get that boost. Next stop, it's going to get that boost, and it'll go through the island, right? So the transport authorities is working on that right now. Okay, let's skip that. This is just making a point that in order for all of this for us to happen, we need a more robust communication infrastructure, because the future is all about how do we very effectively manage all these resources in real time. That requires tons of information. That requires, advanced communication infrastructure for it to be successful. The other aspects that we're looking at is artificial intelligence, of course. We don't want, with tons of this data now starting to come, we don't want to have a person looking at it and making predictions. We want the system to get the input of all this data, make meaningful decisions, and then learn from itself. Constant learning is another interesting, challenging, exciting challenge that's coming to us. All right, so real quick, what do we have? What are we doing today to kind of build the future workforce? Realizing that the future is not just about one part of the system, that it's about multitude. We've developed what we're calling a engineering development program. So if you guys are interested, as you graduate, you come into the utility industry. Instead of historically being placed in one particular department, say substation or transmission or distribution, we're now giving you exposure to the entire company. Because really, truly, to build the future engineer, you need to understand a much broader perspective of the whole electric system. So we're, right now we've hired 20 engineers this year. We're going to hire another 20 next year, and this probably would continue. The cycle would continue. The demand is just, it's remarkable. It's, in my experience, past 15 years in this industry, I haven't seen this much hiring happening this rapidly. New departments are being built. The DER planning that I was talking about earlier is a brand new department that never existed before. It's to facilitate these interconnections of renewables to our system. We also realize that to be successful, in addition to just being engineers and learning the technical aspects, you need additional broader knowledge. So we're giving our 20 engineers that we've hired leadership exposure. We're giving them shadowing opportunities with departments that engineers historically were not part of. Regulatory, our customer care, our system operators, the linemen. So you get really a holistic view. So I just wanted to kind of highlight that you guys are relative. This is you guys are new freshmen right now, but keep a lookout for the energy industry because, like I said, what was happening in Silicon Valley in the 90s is what's happening to the electric industry now. It's going to continue to happen at least for the next couple of decades. In addition to this, you should also look at internship opportunities. I'll send you information. Summer is before next summer comes. We're going to be opening up some internship opportunities in a couple of months. Take a look out for that. If what I just talked about excites you, you think you want to explore a little bit more of this, definitely look at the summer internship opportunities that we have. And we try to do the same thing, give interns kind of that broad, holistic view so that they leave the company with not just one, but a broader perspective. So, you have 5 minutes left?
3 minutes.
3 minutes left. All right. So
we
I
can
talked. Okay. So this is what I'm going to do. I'm just going to show you a couple of slides, and then I won't show the video. Does anybody have questions as I go through this? Questions? No. How about we do this? I'll stay after for a little bit, and if you have specific questions, we can address it. On the distribution side, so I talked a lot about renewable. That was one part of my job. The other is distribution engineering. So aside from all of this that's happening, the traditional load is still increasing, right? You go to Boston, you see cranes all over. New buildings are emerging. That is still our responsibility. That is still what a lot of my engineers work on. So I just wanted to give a couple of those examples. Logan Airport is expanding. This is one project we're working on. We're building a new station just for them. We're extending new lines dedicated just for the expansion of the airport. So the engineers get this great opportunity to work with these developers, the building owners, the politicians that are promoting all of this. There's a lot of this community aspect to what our distribution engineering group does. There's a couple of quick designs of what they produce. Another few examples, and then very lastly, the other interesting thing that's happening is electrification of the vehicle industry. Right, EVs are emerging everywhere. So the last thing that I wanted to just touch base on real quick is, as a utility, of course, our engineers are heavily engaged with all of the different companies on the both that are developing the chargers and those that are producing the vehicles, to understand every vehicle's dynamics, needs, and then and building the infrastructure to install charging stations across the state. So, and there's a couple of pictures of what those end products sort of look like. So there's a few charging stations that we've installed in some of our areas. And so that's about it. I wanted to kind of give you kind of a broader sense. And again, I just touched on maybe 2% of what the engineers are going through. There's a lot of interesting stuff. I haven't even talked about the environmental issues that we deal with, where the challenges that environmental issues bring. That, for example, we're building a new line in Boston near the harbor, and there's a turtle population that we have to be careful of. And to make sure that we don't disrupt that or their breeding, we can only work for a very limited time to build that new line throughout the year. It's a very limited scope. So outside of that, we gotta let the turtles do their thing, right? So that's just another aspect of what the engineers go through the whole permitting process. So that's about it. That is it.
Well, let's thank our speaker, folks.
So I'll stay. Any questions? Feel free to. Yeah, go ahead.
The offshore wind, I was trying to the facility. So, question I wanted to ask is that, so like with the offshore wind, there's going to be a lot of, let's say, really powerful compounds that spew out a lot of CO2. Like the building of it is going to be a pretty large carbon footprint. How long is it projected to take for that? What do you call it? For the power that it produces, and the power that it produces to offset the building of it?
It's a great question. So, to be honest, I wouldn't know the actual number. One thing I would say though is to avoid some of the transport issues. Right now, there's only a handful of ships. I think there's only 4 or 5 in the world that can transport the large, the wind, the parts of the wind generators. And all of the production is happening in Europe. To facilitate the New England installation, part of the partnership that we made with Ørsted, we also decided to invest in rebuilding the port of New London down in Connecticut. We're revamping it to bring industry that would produce those parts in New England to avoid some of the transport issues. And then, of course, once it's built, the next 50-year maintenance, right? We didn't want it to be in a situation where we're relying on Europe to supply the parts. We wanted to build them right here in the U.S. So we took that initiative, and one aspect of that decision was to cut down on some of the carbon issues associated with the transport. But I wouldn't know the exact number. Good question.
Folks. All right, let's wrap up.
All right, thank you.
Thank you. Now discuss about the project next week, okay?